Good day, my wonderful viewers. You are welcome to Understanding Chemistry by Nkechi. Today's topic, we're looking at standard electropotential and electrochemical cell. Okay, let's start with the electropotential. When a metal is dipped into a solution of its salt, we have what we call a half cell. Half cell. So this is a metal dipped into the solution of its salt. So two things are possible here. Some of the atoms on the metal, from the metal, will ionize and go into solution to become positively charged ion. So leaving behind its valence electron on the surface. So you have excess negatively charged. So this electrode will become negatively charged on the surface. So remember, the metal ionize to become positively charged ion. So it means that in the solution you have excess positively charged ion. So it means that the solution will be positively charged while the electrode will be negatively charged on the surface. So that can also happen if the ions from the solution accept electron from the metal, from the electrode. The ions from the solution accept electron from the electrode and become deposited as a neutral atom. So if you accept electron from the electrode, it means that the electrode will be positively charged. It means that the electrode will be what? Deficient of electron. So the electron will be positively charged on the surface. If the cation accept electron from the electrode, it means that the solution will have excess anion. So which means the solution will be negatively charged while the electrode will be positively charged on the surface. So the first one that I said of the metals ionizing in solution. Ionizing, let me use a univalent metal. If the M is a univalent metal. That's why I mentioned of the some atoms on the electrode going into solution and leaving behind its valence electron favors metals that are above hydrogen in the chemical series: sodium, zinc. Then the second one, if the cation accept electron and become deposited as a neutral atom, is common with metals below hydrogen in the electrochemical series. Okay, let's look at electropotential of zinc. This is zinc rod. Zinc rod dipped into zinc tetraoxide, a soluble salt of zinc. So what happens that, like I mentioned the first one I did, that the first equation I wrote favors metals that are above hydrogen in the chemical series, and the zinc is one of them. Okay, so some atoms from this zinc rod will ionize to form zinc ion, a positively charged ion, leaving behind its valence electron on the surface of the zinc. So it means that the zinc rod will be negatively charged because it has excess and excess electron. So it will be negatively charged on the surface. Remember, it ionizes inside the solution already. You have zinc ion and sulfate ion. This electrolyte, it ionizes to form this zinc ion and sulfate ion. So what it means that if the zinc atom, some atom from the zinc ionizes to form a zinc ion, it means you'll be having excess of positively charged ion in the solution. So the solution will be positively charged, whereas the rod will be negatively charged on the surface. A potential difference known as electropotential of zinc is set up between the zinc metal and the solution containing its ion. Okay, let's write an equation for this. So zinc metal give up its valence electron to form zinc ion. So let's look at the electrode potential of copper. So this is copper 2 ion / copper system. So copper rod, when copper rod is dipped into copper 2 tetrasulfate 6, what happens is that, remember this copper 2 sulfate as an electrolyte. So inside the solution you have copper 2 ion and sulfate ion. So copper 2 ion is going to be the cation, is going to accept electron from the copper rod and become deposited as a neutral copper. So it means that this rod is deficient of electron. So it's going to be positively charged on the surface. The surface of the rod is positively charged. So what happens to the solution? If this copper 2 ion accepts electron and becomes deposited as a neutral copper, it means you'll be having excess of the anion. So it means that the solution will be negatively charged. So when I write this equation, it means that this copper 2 ion accepting electron to become deposited as what? As neutral copper. So when this happens, a potential difference known as electrode potential of copper is set up between the copper metal and the solution containing its ion. Hydrogen electrode. So the electrolyte has a concentration of 1 mole per dm cube of hydrogen ion, that's hydrochloric acid. So this is a platinum foil, copper and platinum black, and this is platinum wire. So when we pass hydrogen gas at 1 atmosphere into the electrolyte, bubbles of hydrogen gas is seen around the surface of the on the surface of the electrode. And hydrogen electrode have been chosen internationally as a reference electrode, and the value of 0.0 volts. The value of 0 volts has been assigned to it. So it's very difficult to measure the standard electrode of metals in isolation. So normally compare it with that of hydrogen electrode because the value is 0. So when you put the half cell for copper, I use the salt bridge to connect it. Whatever reads in the voltmeter shows the value of the other metal. So that's what we're doing at measuring the standard electrode potentials of metals. So we use copper as an example. Let's look at the definition of standard electrode potential. As I said earlier, that standard electrode potential of any metal ion / metal system cannot be determined in isolation. So it has to be compared with that of standard hydrogen electrode, being assigned the value of 0 at all temperature. So standard electrode potential is a measure of the tendency of an element to form ions in solution relative to the tendency of hydrogen atoms to form ion in solution at standard condition. So for you to score in this definition, this thing must be present at standard condition. So what is standard condition? It means it's taking place at 25 degrees Celsius, or if you come to Kelvin, 298 Kelvin, 1 atmosphere, and 1 molar concentration. So temperature, pressure, and concentration, they are the factors that can affect the value of standard electrode potential. Temperature, pressure, and concentration. So if you want to say at standard condition, what it means that you will say forms ion in solution at 298 Kelvin, 1 atmosphere, and concentration. But I want to say standard condition, you can cover what's inside the bracket. Standard electrode potential of a metal ion / metal system or metal half cell So we're using copper as an example. I want to determine the standard electrode potential of copper. So this is a copper electrode deep in copper solution, copper 2 ion. So this standard hydrogen electrode connected with a salt bridge. So this is a voltmeter. The voltmeter shows a reading of 0.34 volts. This value is the potential difference between the two half cells. So remember, hydrogen has been assigned a value of 0 volts at all temperature. So this value shows, since hydrogen is 0, this value is for this half cell. It's for the half cell. So what it means that the value could be either positive or negative. So the value is positive if electron flows from hydrogen electrode to the metal ion / metal system. In this case, you can see the electron flow. Electron flows from hydrogen electrode to that of copper. So the value is going to be what? Plus. That's why if you see the standard electrode potential of copper, it's assigned plus 0.34 volts. So if I put another metal that's more electronegative than hydrogen, for example, iron electrode, zinc ion / zinc system or zinc half cell, you can say that zinc is more electronegative than hydrogen. Electron is going to flow from zinc to the hydrogen electrode, and the value is going to be minus. So it means that element is capable of what? Reducing hydrogen. Let's look at the equation of reaction at the electrode. So at the platinum in hydrogen electrode, you can see the hydrogen gas. This is the hydrogen gas that has been bubbled into the electrolyte. It's oxidized to hydrogen ion. So you can see it loses 2 electrons. At the copper electrode, copper 2 ion is reduced to metallic copper. So that's reduction at the copper electrode. So let's write the overall reaction. So overall reaction, the electron will not appear there. You cancel the electron and add the two equations together. So the electrochemical cell. So as you can see, this electrochemical cell, this is an electrochemical cell. The difference between these two, this and this one, a porous partition separates the two half cells. In this case, salt bridge separates the two half cell compartments. So you can see zinc rod or zinc electrode is dipped into the solution of its salt. Copper rod is also in contact with its solution, and the electric current flows through the wire that connects the two electrodes. So what happens is that the function of this porous partition is to prevent the two solutions from mixing together. But it allows movement of ion from one compartment to another. So what happens is that some atoms in the zinc rod is going to undergo oxidation and lose 2 electrons, each 2 electrons on the electrode. So what that happens, it means that it loses 2 electrons to form zinc ion in the solution. The zinc ion inside in the solution. So it means the electron, you're having excess electron on the electrode. So the excess electron that is deposited on the zinc rod moves along this conducting wire and enters the copper electrode, which is deficient of electron. The electrolyte in this compartment is copper 2 ion and the sulfate ion. So what happens is that the copper 2 ion is going to accept 2 electrons from the copper electrode, have become reduced to metallic copper, which is deposited on this electrode, leaving behind excess anion, excess of sulfate ion. So remember, in this compartment, zinc ion is being produced because the metallic rod, some atoms from the rod lose the electron and become oxidized to zinc ion. So it means you have excess zinc ion. So this sulfate ion that's excess in this compartment is going to flow along this, is going to move into the other compartment through this porous partition. Porous partition allows movement of ion. So this excess anion, sulfate, is going to move along this through the porous partition in order to complement this excess zinc ion that you have there. So when this happens, electrical neutrality is maintained in the both solution. Okay, so you can see in some textbooks they put the cathode is on the other side and the anode is here. It does not matter. What matters is that whether you place your cathode here or you place your anode here, so what matters is the flow of electron. Electron flows from the anode. So you can see the direction of a flow of electron here. It flows and enters here. Even if your anode is here and your cathode is the other side, you just what you need to do is just put the flow of electron. You just show that like this, okay, moving like this. That's what matters. So it does not matter. Maybe I seen this in your own textbook. They put zinc rod is the other side, and it does not matter. What matters is the flow of electron when you draw the thing. So look at this one. The cathodes, I place the cathode here and the anode here. So you can see the direction of flow of electron. Electron is flowing from this zinc electrode, being the anode flows. You can see the direction of the flow of electron. So this is something we ought to do on the other side. Salt bridge connects the two together, two cells together. So this is copper rod deep in copper 2 6. Zinc rod dipped in zinc 6. Zinc 6 aqueous. So this salt bridge is a filter paper soaked in potassium chloride, sodium chloride, or ammonium trinitrate 5. So what happens? Essentially, what we did here, the other thing. Some atoms in zinc rod will undergo oxidation and lose 2 electrons to form zinc ion in the solution. And the valence electron will be on the surface of this electrode. So what happens is that this excess electron is going to move along the copper electrode, which is deficient of electron. Copper 2 ion in the solution will migrate to this electrode and accept the electron and become deposited or reduced as metallic copper, leaving behind this excess excess anion in the solution. That's sulfate ion in this solution. So what happens? Since sulfate solution is excess, remember this your salt bridge is soaked with sodium chloride and potassium sodium chloride. So the ions there, sodium ion and chloride ion. So because I have excess sulfate ion in this solution, the sodium ion is going to migrate here, move here to do what? To balance it. Because the other time we have excess of SO4, sodium, I see the sodium ion coming in to balance it. Then what happens to this one? The zinc ion. Since zinc atom undergo oxidation to form zinc ion, it means you're having excess zinc ion. The zinc ion is in excess. So the chloride ion from the salt bridge will also migrate, come in to do what? To neutralize it. In that case, electrical neutrality is being maintained in both compartments. So this salt bridge, what's the function of salt bridge? Is to maintain electrical neutrality, or to complete the cell electric circuit and maintain electrical neutrality. It also allows movement of cations and anions in both half cell. So, like I said, if you are given, for example, you can be given an equation maybe to draw a electrochemical cell where you are given maybe two metals. Maybe you are given magnesium and silver. The one that is more electropositive in the chemical series, magnesium is higher than silver in the chemical series. So that one that is higher is going to serve as the anode. The one that is lower is going to serve as the cathode. Let's look at the equation of the cathode and the anode. And also know that when you have two half cells connected with sub-bridge or porous partition, the electromotive force of that cell must be calculated. So let's look at the equation at the cathode and the anode and overall reaction. Equation at the zinc electrode at the anode. Of course, oxidation takes place at the anode. So zinc give up its electron and has become oxidized to zinc ion. So at the cathode, reduction takes place at the cathode. You can see the copper 2 ion is being reduced to metallic copper. So the overall reaction, it means the electron are going to cancel out the electron. So overall reaction is zinc plus, add the two equations together, copper 2 ion, zinc ion plus copper. The reduction potential for copper being plus 0.34 volts. This is reduction potential for zinc. And the two half cells are in their reduction potential. So we want to calculate the electro potential of the cell. E cathode, the one that is sound as cathode is the copper. The one that sound as anode is the zinc. It's sound as the anode. So the E cell. So what's the value for the E cathode? 0.34 minus the one for the anode is this, and it's a minus sign, so this bracket to enclose it. So the E cell 0.34 minus times minus will give us plus. So the E cell will have plus 1.1 volts. If you have to use this formula, you must ensure that the two half cells are in their reduction potential. They must be in their reduction potential for you to use this formula. What happens, for example, for instance, if this is written like this one is oxidation potential, and you are giving plus. Don't just rush to put this on to write. If I give a question like this, first you have to find out, okay, are they in their oxidation potential or reduction potential? Look at this one is in its reduction potential. This one is oxidation potential. This one is showing oxidation potential. So what we need to do is to bring it up to be in the reduction potential. If you want to do that, you are going to reverse the sign. Now this one is in oxidation potential and the sign has changed to plus. And if you use this formula, you will get this answer. Let's try it. If you put 0.34 minus 0.76, you'll be getting a negative sign, which is wrong. Even if you bring this one here as a 0.76 minus 0.34. You still not get the answer. So you must ensure that their reduction potential. If this is like this and I want to use this formula, what I'm going to do, I'm going to reverse this sign, this thing. I'm going to reverse what is given to me and bring it to the what? Reduction potential and put it in this form. So what will I do next? I'm going to reverse the sign. So it will now be minus 0.76. When you change what is given to you, when you reverse the equation, you must also what? Reverse the sign. This is another formula to solve this. Standard electric potential of the cell. Electric potential of oxidation plus electric potential of reduction. So when do you use this formula and when do you use this one? Like I mentioned before, you use E cathode minus E anode. The two half cells must be in the reduction potential. If you have to use this one, this oxidation half cell will not be in reduction potential. See the one of B, this reduction. This is reduction, which is the cathode, this is reduction. But oxidation, for example, the copper is given like this. This is the copper. The copper is given like this. So I do potential for the copper. Okay, look at this. These two are in the reduction potential. If you cannot use this formula to solve this, you cannot use E oxidation plus E reduction. Using it when two of them are in the oxidation potential. So if you're using E oxidation, the oxidation half cell, this is the anode where oxidation takes place for the zinc. You have to reverse it because this is showing reduction potential, reduction equation also showing. So if I use E oxidation, you're going to bring this one, reverse the sign. Then what I will do is do what? Reverse the sign. Because I've reversed the equation to be in oxidation reaction, oxidation, to show oxidation reaction, I'm going to reverse the sign. This is minus 0.76. I will reverse it. It will have a plus 0.76 volts. So when I'm solving this, I will now use this value for E oxidation. I will now put 0.76 plus this one is in a reduction potential, which is reduction good 0.34, and I'll get the same answer 1.1 volts. But if you use E oxidation plus reduction and you use it when two of them are in their reduction potential, it will be wrong and it will cause confusion. So students who don't understand this very well, you know, sometimes they get it, sometimes they will not get it, and they'll be confused. So when no one to use anyone that works for you, you stick for that. If it's this cathode minus anode that understand very well, you use it. Just know that you're using cathode minus E anode. The two half cells must be in their reduction potential. If you have to use oxidation plus reduction, and the one of oxidation, the one that's supposed to be the anode, if it's written in a reduction equation, reduction, reverse it, change this and reverse the sign. Simple. Okay, let's look at this question. Draw and label a diagram for an electrochemical cell made up of silver ion made up of silver and magnesium. So the electric potential for silver is plus 0.8 volts. The one of magnesium is minus 2.31 volts. You can see they are in their reduction potential. So question number 1, number 2, okay, write the cell notation. Write the overall cell equation. Calculate the EMF of the cell. Calculate the standard Gibbs free energy. So let's start from question number 1 to draw and label a diagram for the chemical cell. When you have two half cells, these two half cells. What you should note, which one should be the anode and which one should be the cathode? Of course, magnesium is higher than silver in the electrochemical cell series. So magnesium will have to serve as the anode, while silver will be the cathode. You can also use their value, potential value, to know. So look at this one. The one with the higher value will serve as the cathode. So this one is minus, the one and have plus. When you have plus and minus, the one with the positive value is going to serve as the cathode, while the one with a negative value will serve as the anode. When you have two positively, if you have two electrode potential and the values are plus plus, the one with the higher value for plus plus, for example, this is silver, and you are giving copper. Copper is also plus 0.34. Good. If copper is plus 0.34, this is copper plus 0.34 volts, and silver is 0.0 volts. Look at it. Copper is 0.34 volts, silver 0.80 volts. When you have these two half cells, which one should serve as the anode and which one should serve as the cathode? The one with the higher value for when they are plus plus, this one that is higher, the value is higher, is going to serve as the cathode, while this one with the lower value is going to serve as the anode. This is the first question. We are asked to draw the electrochemical cell for the two half cell. So you can see, silver is my cathode, silver rod is the cathode. Deep in the solution of, which sort of silver is soluble? Silver 2035. If you want to use silver 2035 solution, you put silver ion aqueous. If I look over silver, something like silver 2035 solution, silver ion aqueous. Instead of using the wrong salt, for example, using silver chloride, which is wrong electrolyte, it's not soluble in water. So look at this. So 1.01 molar solution of silver ion aqueous. So to connect a salt bridge, you must ensure that the salt bridge is connected deep inside the electrolyte. Don't allow it to hang here. So instead you just draw something that's not deep inside this thing. So this magnesium rod is the anode. 1 molar concentration of magnesium ion, Mg2 plus, you put aqueous. So another important thing is electron flow. You can see that the electron flows from what? From the magnesium, from the anode. You can see this, the sign. So this electron flow. So electron flow. So this salt bridge. Don't use direct current. Don't use battery. When you don't have the chemical cell. So this voltmeter. So this is the first equation. First question. So next one I'm going to look at. To write the cell notation or cell representation. So like I mentioned earlier, cell notation, the anode, you write it to the left. You start with the anode. Oxidation half cell. So this magnesium oxidized to magnesium ion connected to salt bridge. Then silver ion is reduced to silver metal. So this is the cell notation or cell representation. So next I'm going to write is the overall cell equation. We're going to write the overall cell. In writing the overall, we're asked to write the overall cell equation. Electron loss was equal to electron gain. Magnesium loses 2 electrons, and silver here is showing silver has added 2 electrons, but it's showing 1. So I'm going to balance the electron. So I'm going to use this 2 to multiply here. So you have 2. So you have 2 here. You have 2. So electron gain is equals to what? Electron loss equals electron gain. So our overall reaction. Overall reaction. We'll add the 2 together. So this is the overall reaction. If you did not use 2 to multiply this thing, this, if there's no 2 here, no 2 here, you won't get a full mark. So let's take note of that, especially when you have a univalent ion and a divalent ion. So here of the cell, so E cathode. So which one is the cathode? That's silver. E cathode minus E anode. So remember in the equation we are given a magnesium minus 2.31, silver is plus 0.80 volts. All of them are in their reduction potential. Like I said, if you have to use E cathode minus E anode, they have to have same must be in their reduction potential. So our cathode is silver, so we have 0.08 minus, so the anode is minus 2.31 volts. .08 minus times minus is plus. So the E standard will be plus. If you add these two together, I have 3.11 volts. Alright, so I want to say something. If you are asked to find the EMF of a cell and it's plus, positive, this value means a lot. If the value of EMF of a cell or standard electric potential of a cell is positive, it means that that cell is spontaneous. It means that the way you place it is okay. If you get negative value, it shows that what you made the cathode is not supposed to be so. If, for example, I put silver as the anode and put magnesium as the cathode, I'll be getting a negative value, which shows that that reaction is not feasible. If you want to make it spontaneous, make it to work, reverse it. So what are the importance of the value of EMF of a cell? So number one, it helps us to predict the direction of a chemical reaction or feasibility of a chemical reaction. Number two, it helps us to determine the EMF of a cell. So number three, it also helps us to determine the value of the unknown electrode potential. This is the chemical formula. E is equals to E cathode minus E anode. If you are given this value, for example, that the EMF of this cell is 3.11 volts, and you are asked to find the one for the anode, electrode potential value for the anode, you just make this one sort of formula and you get it. Alright, so let's look at the third one, the last question, to find the Gibbs free energy. So this is the formula for Gibbs free energy. Standard Gibbs free energy. This is the formula for standard Gibbs free energy. Look at this. So the formula is minus N V E cell. This N is number of moles. F is Faraday. Then this standard electrode potential. Our N, when we did the overall reaction, what was the number of moles of the electron we got there? So it was 2. The number of moles that we cancel out, we have just 2 electrons. That's 2 moles of electron. That's number of moles. Number of electron, number of moles of electron. So 2. This F is Faraday, 1 Faraday, 9600 Coulomb. So this is the standard Gibbs free energy. This is standard Gibbs free energy. The formula is equals to minus NV E cell. This N is the number of electron, number of moles of electron. This is Faraday. This is the E cell. So this N, when we do the overall reaction, the number of that electron will cancel out. So that's N, 2 moles of electron, 2. F is 96500. That's a 1 Faraday. So this is the E cell, which we got as plus 3.11 volts. So when I apply this formula, we're going to have minus 2 times 96500 times 3.11. So we're having minus 6023 joules, or minus 600.2 kilojoule. So remember, if the Gibbs energy is negative, it means that the reaction is spontaneous. If it's plus, it's not spontaneous. So it means that this cell is electrochemical cell is spontaneous. Let's look at a primary cell. We are looking at electrochemical cell, types of electrochemical cell, primary cell and the secondary cell. So primary cell examples include the Daniell cell, Leclanché cell, clock battery, bicycle lamp battery, torch battery, radio battery. Any battery that cannot be recharged, any cell or battery that cannot be recharged is an example of a primary cell. So secondary cell include lead acid accumulator, which is something as car battery, lithium ion battery, that's phone battery, fuel cell, nickel ion cell, cadmium nickel cell, aluminium air cell battery, rechargeable torch battery. Any battery that can be charged, anything, any appliance you have and it can be charged. You can say rechargeable torch fan battery or fan battery, a torch battery. Alright, so let's look at the difference between secondary cell and primary cell. Primary cell can be recharged. Secondary cell cannot be recharged. Reactions in primary cell are not reversible. Reactions in secondary cells are reversible. Primary cells do not last long. Secondary cells, they last long. So in primary cell, we're looking at Daniell cell and Leclanché cell. The secondary cell, we're only looking at lead acid accumulator. Look at the electrochemical cell, examples of electrochemical cell. We will look at examples of electrochemical cell. So in this case, example number one, example Daniell cell, which is a primary cell. Primary cell and secondary cell, they are all electrochemical cell. So as you know that electrochemical cell and electrochemical cells are used to generate small current of electricity for everyday use, both in home and in industry. So Daniell cell is one of them. Electrochemical cell is made up of zinc and copper. It's called Daniell cell. Daniell cell consists of a copper vessel filled with saturated copper 2 tetraoxide solution. Then you have a porous pot filled with zinc tetraoxide. Then immersed in this solution is zinc rod. So what happens is that the zinc rods, some atoms in this zinc rod is going to undergo oxidation and give up the electron to form zinc ion in the solution. So which also means that the copper 2 ion in the solution of copper 2 sulfate is going to accept the electron and become deposited as metallic copper. The initial EMF or the standard electrode potential of Daniell cell is 1.1 volts. So look at the reaction that takes place at the electrode. So at the cathode, copper 2 ion accepts the electron and becomes deposited as a metallic copper. Then at the anode, zinc loses the electron and becomes oxidized to zinc ion. Let's look at another primary cell, the Leclanché cell. So you can see here is a zinc vessel or zinc container serving as the anode. This zinc terminal serving as the anode. You have carbon rods serving as the cathode. So this is what we call muslin bag or paper liner, acting as a porous partition. All right. So here is the electrolyte. This is ammonium chloride paste. You can call this a dry cell. We have dry cell and wet cell. So this dry cell is made up of a paste of ammonium chloride, zinc chloride, in form of a paste. If paste means that a little water is added to make it to be pasty, because electrolyte conducts electricity when they are in molten form or in solution. Then you also have the manganese 4 oxide. And this is a sealing wax. It helps to do what? To prevent evaporation of water from the electrolyte. That's the function of this seal. To prevent evaporation of water from the electrolyte. So what happens is that the zinc container gives up its electron and becomes oxidized to zinc ion. So when we get oxidized to zinc ion, it means that it's leaving its excess electron on the surface of the zinc. So that excess electron on the anode. Remember, the anode now is having excess electron more than the cathode. So the excess electron on the anode moves through the circuit. This moment of electron produces electric current before it arrives. Electron arrives at the cathode. So what about the cathode? The ammonium ion accepts the electron and become reduced to ammonia gas. So at the anode, what happens there? The zinc rod atoms on the zinc anode become oxidized by giving up the electron to form zinc ion. So at the cathode, this is at an anode, reaction at the anode. So at the cathode, the ammonium ion accepts electron, become ammonia gas and hydrogen gas. So let's balance it. So it's balanced. So you can say hydrogen gas isn't produced. This hydrogen gas isn't produced is being prevented by manganese 4 oxide from adhering to the cathode. So the function of this manganese 4 oxide, remember manganese 4 oxide is a oxidizing agent. It will oxidize this hydrogen gas to water. Or the function of manganese 4 oxide is to prevent the hydrogen gas from adhering to the cathode. So we should call that manganese 4 oxide is acting as a depolarizer. So the function of manganese 4 oxide, take note of that. You can be asked to state the function of manganese 4 oxide. The function of manganese 4 oxide is acting as what? As a depolarizer to prevent the hydrogen gas produced from adhering to the cathode. So this is the equation at the anode and the equation at the cathode. Okay. So the EMF of the cell of this cell is about 1.4 volts. A fully charged lead acid accumulator, the cathode is lead 4 oxide and the anode is metallic lead. The electrolyte is dilute H2SO4. EMF of the cell when it's fully charged is 2.2 volts. And the density of the acid is about 1.25 gram per cm cube. So we're going to look at what happens when this cell is discharging. After discharging, it needs to be recharged. We also look at what happens when it's being recharged. The cell is discharging. Atoms of the metallic lead ionizes and releases 2 electrons to form a 2 ion. So this Lead-2 ion combines, remember the electrolyte is H2SO4, so these are the ions present, hydrogen ion and sulfate ion. So the Lead-2 ion that has been formed is going to combine with this sulfate ion to form Lead-2 sulfate, Lead-2 tetraoxide. This electron has been released will pass through round an electric circuit as electric current, which will be used to start the engine of the car and to light up the lamp of the vehicle before arriving at the cathode. So what happens at the cathode when the cell is also discharging? What happens at the cathode? Lead-4 oxide is going to accept the electron. Lead-4 oxide reacts with this hydrogen ion from the acid and accept electron and become reduced to Lead-2 ion and water. So this Lead-2 ion will also combine with the sulfate ion in the electrolyte to form Lead-2 tetraoxide. As you can see, the anode is already covered with Lead-2 tetraoxide. The cathode is the same thing. So when the both electrodes are covered with Lead-2 tetraoxide deposit, the cell will stop discharging. And to make it discharge again, you have to recharge it. So let's look at what happens when the cell is being recharged. Of course, you want to recharge the cell. That cell will be serving as an electrical cell because you don't recharge it by passing direct current through it, by passing another battery, direct current through it. So when the electrodes have been completely covered with Lead-2 tetraoxide, what happens? The EMF of the cell is going to drop from 2.2 volts. It's going to drop to 1.8 volts, and the density of the cell will also drop to 1.15 gram per cm cube. So at the cathode, when the cell is recharging, you can see because the 2 electrodes are covered with Lead-2 sulfate. This is what is formed. Then this Lead-2 ion accepts the electron and become deposited as what? As metallic lead. You can see this equation. When we wrote the one for the anode, this is the reverse of it. Then at the cathode, at the anode, what happens when the cell is recharging? See what is being produced? Lead-4 oxide and the hydrogen ion is being produced. So when this cell is fully recharged, the EMF of the cell is going to what? Come back to normal at 2.2 volts, and the density of the cell will also come back to in full, which is 1.25 gram per cm cube. Look at prevention of corrosion by cathodic protection. Metals corrode, but the corrosion of iron is called rusting. So iron can be protected from rusting by coating it with a metal that is more electropositive than iron. So you can use iron is protected mostly by zinc or magnesium. Tin can also be used to coat iron. So let's look at the corrosion of protection of zinc. Coating of zinc with coating of iron with zinc. Okay, let's look at coating of iron with zinc and that of tin. Which one will last longer? We'll protect it most. Okay, let's look at this diagram. This is an example. If this is an iron object, and you coat it with zinc. When you coat iron with zinc, you call it galvanization, galvanized iron. So this is iron. This is zinc, coated with zinc. So another one, you have the iron coated with tin. protected with tin. So what happens when these two objects are subjected to, maybe it's a rough handled or there's a scratch? If there's a scratch on this object, what happens? If there's a scratch, what happens to them? So we can see if these objects are exposed in the atmosphere and there's a scratch. Remember, there's water vapor in the atmosphere. It combines with the atmospheric chemical side in the air to form dilute acid, dilute H2CO3, dilute nitrate 5 acid, which will be serving as an electrolyte. Remember, acid, bases, salt, they are good electrolytes. So it means that an potential is set up between this tin and the iron, zinc and the iron. So which one will serve as the anode and cathode? The one that is more electropositive will serve as the anode. So in this case, zinc will be serving as the anode and iron will be serving as the cathode. So what happens? Zinc is going to dissolve. Instead of iron dissolving, it's the anode that's going to dissolve, and thereby as it dissolves, it protects the iron from corroding. Whereas in the case of tin and iron is more electropositive than tin. So iron is going to serve as the anode and is going to dissolve in the solution to give off its electron, thereby corroding. Because I dissolve, it means that tin cannot protect it, because iron is going to go into solution and rust. So we can see that rusting of iron is a redox reaction. So that rust there is iron 3 ion, hydrated iron 3 ion. We've come to the end of today's lesson. Thank you for viewing. Please subscribe to my channel, share it and like so that I can get to others. Thank you and have a nice day. Bye.